So as we learned in the first class, we are first going to connect our data acquisition card into USB port. And here today with me, I have an accelerometer, triple axis accelerometer, together with a some shaker. Shaker is going to be used to generate signals, and then we are going to use the accelerometer to record them. So you're not seeing the mechanical setup, but that's something that you're going to see in your lab. Let's start by creating a blank VI, right? We are going to create a project, and the lab view is going to ask us what type of a project that we want to start. We'll go with the blank VI, press finish, and here's again, left is the user interface and the right side is going to be your engineering window. I like to put them left and right orientation as you again, so you can go here, tile left and right. Okay, so as we know, we need to first get a virtual representation of our deck card into the engineering side. But before that, let me create my while loop. So I'm going to right click, structures, while loop. I'm creating a pretty sizable one today because I think we'll need it. So I'm making a big one. While loop is ready. So first we are going to get the deck assistant into this window. Again, I forgot to put the AND argument, right? So I'm going to come to this stop red dot, create a control, and it creates a stop button at the user interface. Now we are trying to use the express tool set, and we know that we are going to input some data, and we are going to say input, and then we are going to get to the data acquisition assistant. Now, when you place the data acquisition assistant, it will ask you what kind of signal that we are getting, right? Today we are using an accelerometer, which is going to give us an analog voltage reading. So we are going to get the analog, we are going to the voltage, and since this is a triple axis accelerometer, I'm going to select channel 0, 1, and 2. These are connected to channel X, Y, and Z respectively. We're going to press finish. And here we have some chance to actually do some housekeeping here. You can see the channel setting. I like to change the names of this because it's just easier to read or easier to work with in the future. So I'm going to say this is going to be X voltage, right? And I'm going to, well, X direction. Okay, and I'm going to put this as Y direction. And the last one going to be the Z direction. Okay. So now we are going to go and select the terminal configuration. Most of your terminals are set up to be a RSE, so this is something that we are going to do by default from now on, so I wouldn't worry about it. So we select everything to RSE. Please note that I selected all 3 channels. We can do them one by one as well, but it's sort of easier. We are going to take a continuous sample. So we are going to take continuous samples, and I want my reading rate to be in terms of hertz, meaning that it is, if it's 1000, that means that it is 1000 readings per second. And first thing I do, I want to try to see if my accelerometer is working. I press run, and I see that I have 2 channels. One is X and Y directions are about 2.3 volts, and I have Z direction hanging around in around 2.7. Go ahead and press OK. I think we are all set up with this. Now this will initialize a little bit, and what it does now is we get a data stream, right, from all 3 channels as the data output. And the first thing that you will want to do is to visualize this setup. And to do this, let's go ahead and create a graph. So I'm going back to the user interface, going to the graph, and I'm going to make a waveform graph. I put the graph here. Um, I would like to housekeep little bit. I would like to extend this little bit. So you just put it with the mouse and extend it. And I will tell this is your acceleration. This way, acceleration signals. So plot 0 is going to be my x direction. So it always goes from channel 0, 1, and 2. We note that the channel 0 was x. So I can say this is x. This is y. And this is z. Okay. So on the engineering side, I'm basically going to put this data stream in the acceleration signal. And now if I run my program, I will see that the my acceleration now exactly the same thing that I've seen before, right? My X and Y channels are hanging around 2.3, and I have a Z channel is hanging around 2.9. Just for demonstration purposes, I'm gonna open the shaker now. You might hear the sound. And as you can see, we have the shaker on and we are reading XY signal and as well as a Z signal. Okay, first thing that we want to do is to understand how can we read acceleration as opposed to voltage, right? So this is a voltage reading right now. So we know that this is in volts. But what we want to do is that we want to convert this to G. So I'm just going to change this to G. But right now, we know that we have a 0G voltage, right, at 2.3 and 2.9. Instead of guessing these values, I'm going to make some operations here so that I can actually know those values. Okay, let me get this guy to the left, top left, there we go. Okay, so let's start with deleting these cables. We not necessarily don't need these cables right now. Okay, so the one thing that inherent in LabVIEW and it's not very well explained is that this data stream that is coming out from DAC Assistant is the combination of X, Y, and Z channels. If you like to manipulate or measure each channel separately, you have to separate your signal. To do that, you are going to come to the Express toolset again. You will go into the signal manipulation, and then you are going to the split signal function. When you drop in your split signal function, it only accepts one signal and splits into one channel right now. You can hover around with your mouse and then sort of extend this to 3 channels. And right now, on the left side, you are getting one signal in, and then it sort of separates to 3 channels. And the program knows that the first channel will be your channel 0, second one will be your channel 2, channel 1, and then the third one is going to be channel number 2. So this will be X, Y, and Z going from top to bottom, okay? So all I'm going to do now is just going to wire my data stream into the splitter, and then now I have access to X, Y, and Z channels separately. So the first thing I want to do now is to read what is my average signal, 0Z signal. In order to measure my baseline value, I need the 2 tools. One is located at the Express toolset again. So I'm going to the Express toolset, going to the signal manipulation, and I am selecting this tool that makes me convert from dynamic data. So if I have a dynamic data stream like I do now, I will have to use this. So I'm going to put this here, and it's going to ask me, it will take an array of scalar data and then reduce it to 1. Basically, it's going to take the time average. and I would like to take the mean of this data, right? So then I'm going to the mathematics toolset, and I'm going to the probability and statistics, if I manage to go there. I'm going to the probability and statistics, and I'm going to take the mean. Okay. So basically now I have all the tools I need to take the mean value. I'm going to get to the channel X. I will connect to the dynamic data type converter, right? And I will put into the mean. So if you see mean has two different outputs, you wouldn't know what they are. An easier way to understand for each tool is to click to this show content help and click onto this thing. This means that the blue one is going to give me the error, and then the orange one is going to give me the mean value. So in this case, I would like to take the mean value, meaning that I will read this top indicator. That's the mean. Here's a trick. If you like to put a indicator here, you have two options, and I will show you the easy one, which is you right click. If you hover around this indicator, it will start blinking, and you are going to click, and you are going to say create, and you can say a indicator, right? This indicator is going to be an indicator at the user interface, as you can see, and we can give it a name as the X mean, right? So that's the mean average of the X channel. So let me do a little housekeeping, put these things together so they look neat, and I can copy this and paste it again, so it will have the same sort of properties, and it also will be indicator. And now I can rename this as Y mean, right? And the third one is, as you guessed, is going to be Z mean value. Okay, so we have X, Y, and Z all waiting to be connected to their respective channels. I will try to be organized and put these little separated, and it will be clear in a minute why we are doing it this way. Okay, and here's our data stream. Okay, so I will rewire these just because I like them to look neat. So now what we should see is going to be the mean values of X, Y, and Z shown in those indicators, averaged over the whole run. So now we are actually missing our acceleration signal, right? Because it was not connected. So we are going to connect this here to data stream again. And that's our signal. Okay. So now if I run my program, you'll see that we have X and Y channels here, and then the Z channel here. And if you look, their mean values are 2.36, 2.37, and 2.88. So now what I want to do is that I want all of them to read 0, right? Because right now they are all under 0G. So the one thing that I can do is to use a numerical operation. To use the numerical operation, I'm going to go to right click, I'm going to go to numeric, and since I want to subtract the mean value of voltage that I'm reading now from the channel, so I'm going to go to the subtract and put one subtraction function here, right? So as you can see, subtract has two inputs and one output. It gives X and Y as an input, and X minus Y is your output. Okay, so what I want to do is that I want to subtract the mean average of that channel from itself so that it will read 0. And I'm going to go to the numeric toolset again, right click, numeric, and I want to do a constant. I'm going to put a constant number here, and I already measured that the X mean is 2.36 volts, and I will punch this number as a constant 2.36, and I will designate it as the Y value, and I will take my data stream, right, coming from here, and I will directly tap into this and minus this value, right? So basically what we are doing now is that we are taking the data stream, splitting to an X channel, and subtracting the average value of X channel from itself and reading an output, okay? And then this output, if you were to read it now, should read 0. How about we do that? So I'm going to right click to here, and we're going to create a numerical indicator, okay? This numerical indicator will be here, and I'm not going to rename it because it is going to be a temporary one. And let's see what happens. If I start my program, I will see that my X mean, which is the one before the subtraction, is 2.36. And if you look at your numeric value, you'll see that it is very close to 0, but since our average is not accurate enough, we are seeing some significant digits after 3 zeros, but we are not going to worry ourselves with that. Okay. So let's delete this numeric indicator because we don't need it anymore. And now I want to do is to do the same thing for the other channels. And pretty much I'm going to select these two, and I'm going to copy them, and I'm going to paste it and carry it over to this spot for this one. And I'll do the same thing once more and carry it over to this spot. And I know that the average of the Y is 2.37, and then the average of Z is going to be 2.88. I have to do some wiring here. I'm going to wire the Y into these numericals, and I am going to wire the respective channels to the main data stream. So in this way now, if I were to read all these, they all should read 0 or very close to 0. And the second thing now we want to do is let's change our graph indicator a little bit, because right now we are reading before we do our signal manipulation. Okay, I will clear this cabling, and I'm going to move this to the right. And as you can see now, this is only accepting one input, but now we have X, Y, and Z as 3 different inputs, right? So we are going to use the opposite of the splitting channel, right? And we are going to look at this in a way such that we are going to go to signal manipulation again and split. Instead of split, we are going to merge the signals. I'm going to put this one here. And I will say I have 3 channels that I want to merge, and I will take this one, let's do it from XYZ. So I'm going to take the X, put it into the first one, take Z, put it into the second one, and put Z and put it into the third one. And if I were to connect this one here and press play, you'll see that your signal is going to be very close to 0. You'll see these peaks here because if you look at our scale is 0.01 and to minus 0.01. So there's some fluctuation depending on the noise from the DAC card. And you already knew that we will have some noise because we measured without any accelerometers last week, and you've seen some signal. Okay, so I have a question for you now, is this signal that we are reading is in G's or in voltages? If you're thinking about this question, the correct answer is voltages, because accelerometer is outputting voltage. But the one piece of information that I have and you don't have access to is that the sensitivity of this accelerometer. And we know that the sensitivity of this accelerometer is about 0.5 volts per 1 G. So how would we read the G's in this program? So I'm going to delete these cables a little bit to open more space. And since we know that every 0.5 volt that we read is 1 G, I will convert the voltage into the G by using that number. So to do that, I'm going to use another mathematical operation. I'm going to divide the incoming channel to the volts per G so that my output will be in G's. So here is again, I'm going to the numerical output or numerical toolset, and I'm switching to divide, right? And I will get to divide, put one here. So our input, so let's read what the divide is saying us, right? So I'm going to go to the help window and click on this, and it takes x and y and gets us the x divided by y. I want to divide the incoming signal by sensitivity. I already know that my numerical conversion factor is 0.497 for X channel. In here, I just copy paste this numerical constant. You can also do this by clicking to numeric and going to the numeric constant. I know that I'm just going to copy this and paste for the Y channel. I know that my sensitivity is going to be 0.503 for my Y channel. And if I do this one more time, I know also that my Z conversion is 0.497. So this is correct. Now I'm going to get the input signals and divide it by the conversion factor. Okay. So now if I want to combine these signals and plot, again, going to X channel to first one, Y channel to the second one, and Z channel to the third one. And I'm going to try to make sure that these are sort of aligned and looking neat. I'm going to put this one here. Okay. So if I start now, as you can see, I'm reading in G's and I'm reading pretty close to 0. And if you were to open this accelerometer, you will see that our Z signal is close to 0, and X and Y channels are giving us around 0.4 to 0.6 peak accelerations. Okay. With that information, now I'm in the point that I will actually try to measure these. You can have two ways of measuring it, right? One way of measuring it is that I'm going to open this again to look at the difference between peak to peak values, right? Or you can use it using LabVIEW, and this is what we are going to do. So to measure this, we are going to go to the Express toolset, and this time we are going for signal analysis, and we are going to measure two things. One is the amplitude and level measurement. I'm going to put one right here. And it is as soon as I put it, it's going to ask me what I want to measure. You have the option of measuring RMS, positive peak, or peak-to-peak accelerations. And all these definitions are given in your lab handout. Please take a look. And during the lab, you will have a chance to use any one of these. Okay. I'm going to click OK. So if I were to look at how this looks, I see that I have on the left arrow, I'm in incoming signal. So this is accepting a signal, and this is giving you peak to peak, positive peak, and RMS as an output. Okay, I'm going to use the same thing for X, Y, and Z because I would like to measure the same thing for each channel. And the second thing that I'm going to do is let's put them a little bit separated. Okay, right there. And then the second thing I'm going to do is I want to measure the frequency. And again, frequency is going to be utilizing Express toolset, signal analysis, and we are going to go to the spectral analysis this time. And I'm going to put the spectral analysis toolsets right here. And it's going to ask me how I want to measure it. First, I want to use a linear result. I have a chance to look at the power spectrum. That's what I want. And that's about it. So I'm going to use the power spectrum using a linear filter or scale. And here it is getting you a signal input and a power spectrum output. Okay. I'm going to connect my incoming signal to my sort of G value, right? And I have the option to read peak to peak, positive peak, and RMS. For now, I'm just going to read peak to peak, but you have a chance to read all of them, and they should all be pointing out to the same true value. Okay, so I'm going to right click to this. I'm going to say create. I'm going to read it using a numerical indicator. It's going to say peak to peak. I'm going to rename it because I know that this is the X channel's peak to peak. So I'm going to say X peak to peak. And I am going to create another one for Y peak to peak. So I'm going to right click, create, and I'm going to say a numeric indicator. And I'm going to rename this as Y peak to peak. And I'm going to do the same thing. I'm going to come to peak output for Z channel. I'm going to say create a numerical indicator. I'm going to rename it as Z peak to peak. Okay. And I'm going to have to do some cabling here. I'm going to put my input signal for this to Z. I'm sorry, to Y, and then I will put this input signal to Z. Okay. So right now I have three numerical indicators. One is X peak to peak here. I'm going to put them here. X peak to peak. Oops. This is going to be Y peak to peak. I'm going to get my indicator number here. Okay. And this is Z peak to peak. Okay. So if I'm measuring the peak to peak values, then my shaker is off. I should be able to read a very small number. It's telling me that I didn't connect the spectral measurements to anything. That is correct. So let's put the spectral measurements into the same input channel. So I'm going to come here, hover around, and connect it to here. Connect it to here. I'm going to connect this to here. Right? You are just tapping into X, Y, and Z. As you see, I just did a little bit of reorganization. So with that, I will start my program, and we will like to see what is the peak-to-peak accelerations in X, Y, and Z. When I run my program, you'll see that the peak-to-peak accelerations are not exactly zero because we didn't zero the channel as accurately as we wanted to do. But as you can see, this is sort of close enough. At least up to one significant digits, it's close enough. And if you like to do this more accurately, you can, but for this demonstration purposes, we are not going to. And then stop this. Now, the next step is to read the power spectrum. And unfortunately, power spectrum cannot be looked at the graphical indicator, and we can discuss this in the lab. But what I will do is that I will create, instead of a numerical indicator, I'm going to create a graph indicator, right? Let's do the indicator create and graphical indicator, right? And it creates a graphical indicator in here. and you will like to rename this X frequency spectrum, and I will want to call this as X, and I will do the same thing for Y. I'm going to get this one here, and I'm going to connect it to this power spectrum output. I'm going to do the same thing here, and I'm going to put this to this spectrum output. And as you can see, every time I do this, I create a new graph. So I'm going to put this graph here, and I'm going to put this graph here. And the naming convention is a little bit different now, right? This is going to be the Y frequency spectrum. And the last one is going to be Z frequency spectrum. Great. And one thing that you realize here is that the graph doesn't know what the units are, right? So this is our power spectrum, and this is the frequency. Even though it says time, it is actually frequency because we are reading the power spectrum. So I'm going to have, this is frequency. I'm going to say this is power spectrum, and this is going to be again power spectrum, and this is going to be frequency. Okay. So, and as you may realize, the frequency has the unit of hertz. So we are going to put the hertz right here as well. So then you actually know what you're measuring. Hertz, and here the other one. Okay, now when we press go, we will read the power spectrum at with nothing is running, and I will also try to limit the spectrum to a lower frequencies. To do that, I will right click to my spectrum, and it gives me sort of options that I can use with this. I'm going to go to the X scale because I'm trying to change the X sort of axis, and I will click off the auto scale, and I say that I want the maximum I want to read to be 10 Hertz. So this is sort of, as you can see, scales back to 10 Hertz, and I will do the same thing for this, and I will do the same thing for that. And at the same time, I will have to come X and close the auto scale, because as soon as I hit run, it will auto scale it. Okay, now when I hit run, I'm limited at 10 Hertz. And let's see what happens if I power up my signal generator. So you can see now the X and Y are giving me a signal, and they are in 90 degrees phase difference, considering X and Y are perpendicular to each other. The frequency of the X and Y are about the same, and Z's frequency is a little different because that's the Z direction. Okay, so I'm going to stop my program, close my shaker, and this is the end of the tutorial for setting up the accelerometer for the accelerometer lab. And then this way you'll able to read the X, Y, and Z peak-to-peak accelerations, as well as visualizing your the acceleration in a correct scale, as well as looking at the power spectrum. And I will see you guys next time.